Modular fixturing is one strategy to use standard components to create fixtures, which is consistent with our design for X principles that we saw before. If we look at modular fixtures, typically you're going to see a base plate, and here you see an example of a base plate with precision holes in a grid pattern. And these holes, some of them will be precision ground and others will be threaded to provide some flexibility in terms of fixture components. So that would support any horizontal elements that we want to place on the plate, such as locators and risers and so forth. To get a vertical orientation of the workpiece, we place what we call a vertical tombstone on top of that plate. So now we have a surface that we can attach fixture elements to and orient it with respect to the tool in a vertical plane. The fixture elements that we're going to add to the plate or the tombstone are interchangeable, and of course they are precision elements, so they tend to be fairly costly. We'll use risers to build up surfaces or heights to support surfaces as we've described before. We'll use edge locators, supports, clamps, and other locating components. Here you have an example of a riser that provides an offset from the plate here, so that again we can attach locators, clamping structures, and so forth to the riser. Here's a classical example where we have a pivot on this stud here and a nose clamp element where we've minimized the surface area that we are clamping on. And you probably can't see it, but we do have locators below the workpiece here to offset the workpiece from the plate. Clearly, we don't want to start machining our fixture plate because these are very expensive and you don't want to ruin the holes here. Here we have a spring wrapped around the Allen bolt that we're going to tighten, and by tightening that we're going to bring a compression force on the surface of the workpiece. So this is fundamentally a lever principle where the pivot, the fulcrum, is right at the stud here. Note that one of the disadvantages of the modular fixtures, especially the plates and the tombstone, is the tendency for these precision holes to gather debris, especially where we have material removal processes such as machining. And so they become kind of magnets for that debris. So what you probably want to do after creating your fixture is cover all the holes so that does not occur. If you look at modular fixtures in terms of cost, they do have that high initial investment because you're buying a lot of standard components and plates, but it will help reduce your tool engineering cost in that we don't have to make custom fixtures for every part that we produce. All we have to do is create that from our standard components. So it tends to reduce the lead time because we don't require that fabrication in getting the new tooling up and running. And since we can break down all the fixtures into their components, we can reduce the amount of storage requirement for our fixtures. So if we have a high product variety environment and typically a low volume in terms of number of parts we're producing at any given time, the modular fixtures lend themselves very well to that because of the advantage of changing our fixture design to accommodate that product variety. And also, if our product designs are changing on a very fast pace, the geometry may be changing, and if that's true, then what we want to do is use a modular fixture to accommodate changes in the design. Note there is a downside along with the high initial cost, and that is your increase in setup time if you have to build the fixture from the base plate or tombstone using your various elements. Let's take a closer look at the clamping forces, such as we saw with the nose clamp there, and how we might try to estimate what those clamping forces are to make sure that we are not going to damage our workpiece. If you look at the issues associated with applying the clamping force, we know that we're concerned about tool forces, and being able to hold the workpiece against the locators. Hopefully, if you know what process you're using, then you can come up with an estimate of the magnitude, direction, and location of the tool forces that are going to be applied. Then if we look at the material, both the material in the fixture and as well as the workpiece, we note that there are certain regions where we'll be clamping and we'll be applying force against locators as well. And then we have elastic deformation. And of course, you know, elastic deformation implies that the material will return to its original shape even though it has been deformed. We're going to apply compressive strain wherever we see locators and clamps, and we should also note that the material itself has internal stresses such that when the material is machined, we might release these internal stresses, and of course that could cause changes in the part geometry. So the approach here is to identify the source of the forces that are being applied and design your fixture elements to oppose those forces. Direct opposition, of course, would be our locators and clamping against those locators. So we would note that we are compressing the material, both the locators and the workpiece itself. So you have to worry about the strength of the materials. Especially the workpiece, we do not want plastic deformation. When we clamp onto the surface, we're going to create frictional forces. As you know, frictional force is determined normal to the force that's being applied to the surface, and it's based upon our coefficient of friction. And in this case, and throughout our discussion, we will only consider static friction. So here we've got a force that's being applied to a workpiece, and when we do that, we're going to have a frictional force, so that if I push against the workpiece here, that frictional force will overcome that force until this force becomes larger than Fs. If you look at steel threads and a bolt face, what you note is that mu is approximately 0.2. And this number is going to be a fraction of the force that's applied in this direction. And that's why we don't like to rely upon this frictional force to overcome our tooling forces. We'd rather use the direct opposition. Well, the lower bound for clamping force, and of course we'd want to incorporate a safety factor or some multiple of that lower bound, is based upon your static equilibrium. And if you recall from your statics, you remember that the sum of the forces has to be 0 and the sum of your moments as well. So you don't want any moments causing bending, and you don't want forces that are not sufficient to oppose the tooling forces. So here's a simple drilling example. I have a workpiece here, and I'm going to take a drill into the slide, and my drill bit goes into the material, and as I do that, the drill is applying some type of torque to the tool, and some of that is being propagated through our workpiece such that the workpiece is going to have a tendency to want to rotate. Now we're not considering any other forces at this point. So when I make contact, some of that is going to be transferred to the workpiece, and it will be dynamic. It will not be continuously the same value. Well, in order to oppose that force, what I can do is place a locator on the corners here, and as you can see, that will prevent the rotation. In terms of the static equilibrium, clearly I've got my forces that need to be 0, and this moment that I'm applying has to be equal to the force at those two distances. So if you look at our fixture design based upon what we see here, then what we'd like to do is to maximize D1 and D2, because if we do that, then that will minimize the amount of force that's being applied at the locator and obviously at this location at the workpiece. So it makes sense to maximize the distance between your locators because that tends to help with the forces that are being applied. Here's another common configuration that we've mentioned before, the strap and bar clamp, and it's based upon the lever principle, as we said before, where the sum of the forces the force being applied to the pivot, the force being applied in terms of axial tension on the bolt, and then the compressive force on the workpiece. Then if we look at our pivot in terms of a moment, we can see we've got a distance of our bolt here from the pivot, that's d sub b, and then we have a distance of our workpiece from that pivot, that's d sub w, so that our moments has to sum to 0. Clearly with the lever principle, you have a mechanical advantage here as d sub b approaches d sub w. What's the implication here? You want to be as close to the workpiece as physically possible with the bolt in the strap bar clamp example here. Now again, you will be limited by the accessibility to that area, but the farther we can move over here, the better in terms of our mechanical advantage of applying a force. So what we'll do is we'll have a flange nut here, and that flange nut will tighten the bolt, and as a result, what's going to happen is we'll increase the tension on the bolt, which in turn applies a force here and here. Well, to understand what's going on there, if you recall from the thread profile, here we have a thread and it's going to come in contact with the thread on the flange nut. And as a result, we're going to end up with some friction here. So we've got some frictional forces that oppose the tightening of the flange nut as it becomes tighter, and then we have to apply more torque. So that's going to be related, obviously, to the angles here, as well as the pitch and the major diameter, because that will affect the size of the thread itself. So as the size of the bolt changes, as the pitch changes, and as these angles change, we're going to get different effects on the clamping force. To understand these threads, you can think of them as an inclined plane. If we take the threads here on the left and unwrap them, and we'll just unwrap one of them around the entire circumference, pi times the diameter, we end up with this inclined plane where this represents the thread itself. And now I'm going to apply a force, again, based upon torque that's being applied in this direction, based on theta, which corresponds to the angle associated with the thread. I will have a frictional force in this direction, and I will be creating axial tension in this direction on the bolt itself. So what we're essentially doing is converting a rotational motion, tightening the flange nut, and converting that to a linear motion, which essentially translates to an axial tension on our bolt. So the bolt threads, if we were to examine them, we have compressive forces on the threads because they're coming into contact with the flange nut. And we're causing axial tension on the bolt. We also have contact surfaces, the head of the bolt or a washer, such as a flange nut, and the threads. Friction is going to be a byproduct of this axial tension, right? We already saw that before, where we apply a normal force and then the friction is at an angle to that. The torque applied to the bolt is opposed by the friction on the thread surfaces and upon that flange nut or bolt head. The resulting bolt tension can vary by up to a range of 30% for the same torque when you have a new thread. So you have to be careful when you create these fixtures that the first time through you tighten and loosen and tighten until you get repeatable tension on the bolt. So here's a very simple model for the tension on the bolt, which would translate to compressive force on the workpiece. If I apply a certain amount of torque, then I'm going to take the tension on the bolt times the distance, again this was the distance from the pivot, and multiply by 0.2. Now 0.2 represents that coefficient of friction, so what we're really doing here is trying to solve for F sub B. I can measure the torque with a torque wrench. I know the distance of the bolt from the pivot, so I can solve for F sub B essentially by inferring that the amount of tension is based upon the amount of friction. So indirectly, we are determining tension via the frictional force. The weakness of this simple model is it's highly dependent on knowing the coefficient of friction very accurately. And in this case, we're just saying it's 0.2. What could affect the friction of the bolt? Well, any lubricants, of course, will have a dramatic effect. Any debris. So there are various factors that could affect the value for that coefficient of friction and throw off this calculation of F sub B. Well, we can also incorporate material effects by using the simple constant model. So I go to a table such as found at the website. You might want to take a look at that. And empirically, I determine the K values by actually collecting data on various threads made of different material. You can see with lubrication, we're going to have a major change in our coefficient of friction versus just standard stainless on an alloy. And then as we change the material properties, our coefficient is going to change. Once we do that, we'll come up with a better estimate of our F sub B, again, the tension on the bolt, which in turn can be used to find the compressive force. Or we could take a look at a more detailed model. And here, essentially what we're going to do is partition the friction contribution from the flange nut as well as the threads. So there'll be friction between the flange nut surface, as you can see here, that will come in contact with your strap clamp or nose clamp. And we'll use the mean radius to come up with our forces related to the flange nut. So as you can see here, it's halfway between the inner concentric circle, which is the through hole, and the outside. So we have an annulus here with a mean radius of r sub n. And then, of course, we have our coefficient of static friction, mu sub s. We have a flange nut moment that we're tightening that, and we also have a thread moment, the threads corresponding to the contact with the bolt threads. So our total moment is going to be T for the thread, or tau for the thread, and tau for the flange nut. If you look at the flange nut moment, it's fairly simple. You have a 2D annulus that's coming in contact, and so the tension on the bolt is going to cause compression of the nut against the surface of the strap clamp. Here we have our R sub n, here's our tension on the bolt, and of course this is the static coefficient of friction. Well, we know this, we know that, we can look it up in the table, and we know this because we have a torque wrench, so we can solve for F sub B. For the thread moment, that's going to be caused by the tension on the bolt, the threads coming in contact with each other. And then we're going to have a friction angle, which corresponds to that maximum angle before one of the thread surfaces starts sliding. So what is that angle? And we'll call that phi. The tangent of phi is going to be equal to mu sub s. And then the average radius of the thread will correspond to 1/2 the pitch diameter based upon what we looked at before in terms of the thread itself. So I've got R sub B for the bolt, and I've got the tangent of phi equal to mu sub s. So my total torque is going to look something like this, where I've got my theta plus phi, again theta from our description of the bolt, and substituting in the tangent of phi is equal to mu sub s. I can then solve for the total based upon adding in the flange nut component. So I end up with this expression by moving everything to the right side. These are all the knowns, given the configuration of the bolt, the material being used, and the torque that's being applied to the flange nut. So the model is a little more complicated, but can be easily calculated. An alternative estimate of the bolt will incorporate the flank angle of the thread. So if you go back and look at the description of the thread and its flank angle, typically alpha is going to be equal to 30 degrees. And we can have separate coefficient for the threads versus the flange nut. That model looks like this. And here we have what corresponds to the flange nut. Here we have what corresponds to the axial tension on the bolt, again incorporating that flank angle. For details of that model, you can take a look at this web page. Well, given that we can calculate F sub B, how could we determine the axial tension on the bolt? Again, if we're in static equilibrium, this is a lower bound. As you can see here, the forces sum to 0, the moments sum to 0. And now I can use my estimate. This was the last model that we just looked at, and solve for F sub B, because everything on the right side of the equation is given. Once I have F sub B, then I can estimate the amount of force being applied to the workpiece over the surface area of the clamp, with the relationship between the sum of the forces and the sum of the moments. So F sub W, the amount of force that's being applied to the workpiece, is just negative F sub B times the ratio of D sub B over D sub W. Don't forget, this ratio of D sub B to D sub W is based upon the mechanical advantage of the lever. Once I have the force on the workpiece, and if I know the surface area, certainly I can get the amount of stress that's being applied to the surface. So here's an example. I've got a bolt and flange nut with these characteristics. Here I'm just using steel with 0.2 coefficient of friction. Again, my alpha is equal to 30 degrees, so 2 alpha in terms of radians is 0.5236. And if I apply a torque to the flange nut of 20 foot-pounds, I can look at the flange nut, and I can look at the bolt, and of course the thread distance is going to change as we move across the different bolt radii. If I plot the force, the axial tension on the bolt, versus on the x-axis the bolt diameter, we see this type of disparity between the models. Again, the approximation model is giving us a bias high in terms of tension on the bolt, and therefore a bias in terms of the force that's being applied to the workpiece. The detailed model and the more accurate one that we just looked at gives us a much better estimate, and so we'd probably want to rely upon that if we're concerned about the clamping force that's being applied to the workpiece. Now, as you can see, as I increase my bolt diameter, the amount of tension on the bolt, and therefore the amount of force being applied to the workpiece, is going down. And that has to do with the configuration of the threads. So for the same 20 foot-pounds that are being applied, if I increase my bolt diameter, my force is going to decrease. Based on that estimate, of course, we could determine if we're going to have any problems in terms of plastic deformation on the workpiece. If I look at a UNC half-inch thread with 13 threads per inch, and I change the torque that's being applied, you can see based upon the models we have a linear relationship between the torque applied and the tension on the bolt. So if I need more tension on the bolt, all I have to do is increase the torque that's being applied, and of course there are limitations to that. Because of that, we don't want to destroy the threads as well as destroying any other components on the fixture. Well, once I know the amount of force on the workpiece in terms of the fixture, I can compare that to the forces that are being generated by my process. Now, if you recall from 248 with orthogonal cutting, you were able to estimate the amount of force that's being applied, and we had a force into the fixture, F sub t, and we had a cutting force in the direction that the tool is moving. And so this is where we'd be concerned about having locators that oppose that force, and of course if we come back in the opposite direction, we would have to do the same thing here with either a locator or a clamp that's clamping up against this locator. Again, this gives you an estimate of what those forces are. You have to consider a safety factor because, as you know, these forces are dynamic. Once I have that cutting force, which if you go back and look at your orthogonal cutting, can be estimated using the characteristics of the tool and the material, then I've got my cutting force estimate, which of course must be opposed with our locators, and we have to also account for any moments that are being caused by F sub c and or F sub t. Don't forget that we want to operate in our stress strain curve in the elastic deformation region. We don't want to be up in this region where we begin to see our plastic deformation, and certainly you don't want to be in that area, otherwise your workpiece can be severely damaged. So this, of course, as you recall, is based upon Young's modulus, which gives us an idea of the amount of strength that we have in this material. And if you recall, compression is in the opposite direction of tension, compression being on the workpiece, tension being on the bolt. Some of the yield strengths that you've probably seen, titanium, obviously one of the strongest materials, will be very high. Typically, you're not going to have a problem with that workpiece. But as you begin to get into the softer materials, you have to be concerned about how much force you're applying over a region. So if you've got a very small region and a high degree of force, then you might achieve this 15,000 pounds per square inch, and that's what you should be concerned about.